All right, we can now start 6.2, which is a section all about setting up different kinds of integrals and really gets at the heart of why integration is useful. And there's a certain way of thinking that really embodies the integral. And it's this idea that you can split things up. So if you have a large problem, something that varies continuously, you can pretend for a moment that it doesn't vary continuously, but there's these little chunks. And if you can break this larger problem down into solving it on all of these little small pieces, then if you make the pieces very, very, very small and you add up lots and lots and lots of pieces, then under some assumptions, the large problem is really just the sum of all of those smaller problems. So take, for instance, that of area. So the first thing here is a cylinder, a cylindrical sort of solid. So here, if our base is this shape, and then we know that this has an area of A, and no matter where we slice this, so if you can imagine that we slice this at some plane, so let's say we draw a plane here, okay, and then we slice the cylinder, it's going to give us exactly the same shape as we have down here. So it's not like it's not like this shape down here where the actual cross section that we get is changing depending on where we make that slice. So if all of your cross-sectional areas are equal, then the volume of this figure is just the area of that cross-section times the height. You can sort of think about starting with this area in the base and then stretching it this distance h. But what happens if our cross-section does change? So unlike up here, what if we have something down here where it's changing size? Okay. So one way we can do this is, again, like I said, this curve is varying continuously. So it's not just that this area here is exactly the same as this area here and the area in between that's not drawn. It varies continuously. So that area is changing constantly. It's perpetually changing. One way that we can get the volume of the shape is to first pretend that we have finitely many little slabs. I'll call each one of these a slab. Okay. So if we have, let's say we have one, so here we're assuming that we have n different little slabs. Okay. In which case we can figure out, we can approximate it with a cylinder. Now truly this is varying. It's not vertical. It could be tilted, or it might even be varying really oddly. But what we can do is just assume that if we have lots and lots and lots of these, so let's say n was, a billion. If I subdivided this up into a billion little slabs, then sure, the top, the area up here is going to be different in general than this area, this cross-sectional area here. But if we have a billion little slabs, then this distance is really small. It's at least as big as this distance here, b minus a, divided by how many slabs we have. So in general, that distance is b minus a over n. So as n gets really big, so like let's say goes to infinity, then this distance here gets really, 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 really small. And that's exactly what they're calling delta y here. We're really saying that this delta y is take the total length, or height of your solid, so this distance here, the difference between B and A, and then divide that by the number of slabs you are partitioning or dividing the solid into. So then we can figure out the volume of this by pretending, or just by using, the bottom area as the area, or even by using the top area here. So we're essentially going to approximate each one of these little slabs with a circular cylinder. So even though the bottom base area and the top base area and the top area are different, as long as we have lots and lots and lots of these, they should be approximately equal to one another. So the basic idea here is the volume of this little slab is the area of either the top or the bottom multiplied by this difference here. So we can say the volume is approximately the sum from I equals, let's say, 1 to n of A sub I. So let's say the top, A sub I, times the change in height. So then this is an approximation, but if we wanted to get a true, what is the, how could we make this estimation not an estimation but make it perfect? We could take a limit. So we could say the true volume V is the limit as n goes to infinity of the sum from I equals 1 to n of A sub I delta y. Well, this right here, in brackets with red, this is just the definition of the integral from Calc 1. It's a Riemann sum. So, oops, let's go back. So this would essentially be the integral from A to B of the cross-sectional area. In general, this will vary, so it's a function of y with respect to y. So volume, V, is the integral of the cross-sectional area. And essentially, that's exactly what we worked through, and that is our theorem here. So to find the volume, we will integrate the cross-sectional area. So for all of these problems, these example problems, such as example 1, which we'll do in the next video, the main goal is to figure out if we are at some height y. So we're treating the plane that the base is in, so this plane here, we're treating this as, let's say, y equals 0. Right, that's right here, y equals 0. So then we're just saying if we go up to some height y, we just leave this y as arbitrary. So we go up some amount y. We want to know how can we write down a formula for this area that only depends on y and, let's say, the values 2 and 4. Our goal here is to come up with an expression, a function for the cross-sectional area A as a function of the height. Then we can integrate this area function to get the volume of this pyramid. All right, we'll do that in the next video.